Hi, I'm Laura Buttle, and over the past year I have been working on a final year project titled Design and Implementation of PCC-OFDM in a 5G scenario at Monash University.
The Internet of Things is a rapidly expanding area of technology, and with the growth of the Internet of Things, we're also seeing a huge increase in the number of machine-type communication devices. Machine-type communication devices, as opposed to human-type communication devices, are devices which allow for the seamless collection and transmission of data between devices and to a central base station or machine-type communication server. The current 4G mobile network requires that there is strict synchronization between the machine-type communication devices and the base station. Along with this requirement, each signal must have an orthogonal training sequence added to it in order to determine the channel characteristics such as carrier frequency offset. In order to meet the increasing demands being placed on the mobile network, 5G is currently being developed. 5G will operate over a much larger frequency range and include much higher frequencies than that of 4G. The waveform that is used for 4G, CP-OFDM, or Cyclic Prefix Orthogonal Frequency Division Multiplexing, has high out-of-band emissions, and this makes it unsuitable for use in high frequencies. It also requires tight synchronization between the transmitter and the receiver, and it requires unique orthogonal training sequences for each device, and this limits the number of communication devices that can be used at once. These are the features which make it unsuitable for use in 5G. Over the course of this project, I have been investigating the possibility of using PCC-OFDM, or Polynomial Cancellation Coded OFDM, as a waveform in 5G. PCC-OFDM has low out-of-band emissions, which makes it better for use in higher frequencies. It also naturally outperforms CP-OFDM in an asynchronous environment. This project has also demonstrated that it can be used without training sequences for carrier frequency offset estimation. The method that I have used for carrier frequency offset estimation is a blind estimation technique, which uses the data in the waveform itself. This eliminates the need for orthogonal training sequences to be added, and this increases the number of devices that can be used at any one time in a machine-type communication uplink scenario.
CP-OFDM is the waveform that is currently being used for the 4G mobile network. As can be seen in the image at the bottom, it has a very square shape in the time domain. This causes high out-of-band emissions in the frequency domain. As we can see in the graph on the top right of the screen, the out-of-band emissions are only 20 dB below the transmission band. In the graph in the bottom right corner of the screen, we can see the CP-OFDM symbol bit error rates over varying signal-to-noise ratios. In the case of carrier frequency offset being present in the channel and no compensation methods being implemented. From this graph, we know that the bit error rates are extremely large and the received signal would essentially be nonsense. PCC-OFDM is a waveform which was first published in the late 1990s. Since then, it has been developed gradually over the years. With the 5G network being developed, PCC-OFDM seems like a natural fit for the high demands of the future mobile network. As can be seen from the image in the left of the screen, the symbol shape in the time domain is much smoother than that of the CP-OFDM. The fact that the symbol narrows at the end causes it to have low out-of-band emissions, which we can see in the graph in the top left. The out-of-band emissions in PCC-OFDM are about 3 times lower than those of CP-OFDM symbols. The graph in the bottom left corner shows the bit error rate versus a signal-to-noise ratio curve in the case of carrier frequency offset being present in the channel with no compensation method. Although the bit error rate is higher than ideal, it is much lower than those of CP-OFDM in the same scenario, and it is possible that the received signal will still be usable. From the comparison of these graphs, we can see that PCC-OFDM naturally outperforms CP-OFDM when there is carrier frequency offset in the channel, as is the case with all channels that are asynchronous. The way that PCC-OFDM works is that it maps each modulated data point onto 2 or more subcarriers. However, in the context of efficiency, using 2 subcarriers is preferred. This was the method used over the course of this project. Each of these subcarriers is weighted differently. In the case of the 2 subcarriers, they are weighted +1 and -1. This means that there is a 180-degree phase shift between them. In its original form, PCC-OFDM is much less efficient than CP-OFDM, since each data point is being transmitted by 2 subcarriers. However, this can be solved by using overlapping PCC-OFDM for transmission. The overlapping method increases the efficiency by almost 50%, and when you consider that no cyclic prefix is needed, then the overlapped PCC-OFDM waveform is actually more efficient than CP-OFDM. One objective of this project was to investigate blind carrier frequency offset estimation in PCC-OFDM communication systems. But what is carrier frequency offset? Carrier frequency offset, or CFO, occurs when there is a difference in the frequencies generated by the local oscillators in the transmitter and the receiver. If we look at this simple example where the signal being transmitted is a sine wave with frequency f, the local oscillators in the transmitter and receiver are used to generate this frequency. However, since they are completely separate, they may not be synchronized, and the transmitter might generate a frequency f plus delta, and the receiver might generate a frequency f minus delta. This would create a frequency offset of 2 times delta. In the image on the left, we can see the signal constellation of a transmitted signal. On the right, we can see that the received signal has been affected by carrier frequency offset from the rotation that has occurred. In the high-end, expensive equipment such as base devices, the local oscillator can be expected to be very accurate. However, in cheaper domestic devices, where keeping the price down is important, the local oscillator is likely to be inaccurate. The use of training sequences for CFO estimation is a well-known and commonly implemented method. In the case of this project, Barker training sequences were the specific type of training sequences used. Barker training sequences are a series of training sequences of different lengths which have specific autocorrelation properties. These are displayed on this graph, which demonstrates that the autocorrelation only has a large output value at one point where the Barker sequences line up perfectly with each other. At any other point, the value is very low. This is useful in allowing us to find the phase difference between 2 consecutive Barker sequences transmitted. The equation which was used to determine the normalized carrier frequency offset from 2 consecutive transmitted Barker sequences is shown here. In this equation, Z1 and Z2 represent the first and second Barker sequences received, and delta Ft is the normalized carrier frequency offset. The term on the top takes the sum of all of the complex conjugates of the first Barker sequence, multiplied by all of the second Barker sequences. The angle of this sum gives us the phase difference between Barker sequences in radians. This value is then divided by 2 pi so that the final value is the normalized CFO. Blind CFO estimation is a method which has been explored for PCC-OFDM over the course of this project. The method I have used exploits the fact that in PCC-OFDM we are sending 2 of the same signal 180 degrees phase shifted apart from each other. In the case that there is any phase difference other than 180 degrees, then we know that this is caused by the carrier frequency offset. The equation used to find normalized CFO in this blind estimation technique is shown here. In this equation, Z2m plus 1i and Z2mi represent the 2 weighted subcarriers of the same data point. Delta Ft is the normalized CFO and n is the total number of subcarriers used. Since each of the subcarriers carry a value with identical amplitude but opposite sign, then when they are added together in the numerator, this value should be 0, causing the overall normalized carrier frequency offset estimation to be 0. However, when there is some carrier frequency offset present, then this value will not be 0 and the output will represent the normalized CFO. The first major objective of this project was to implement and compare 3 different systems in MATLAB. The 3 systems are CP-OFDM, PCC-OFDM with training sequences, and PCC-OFDM with blind CFO estimation. The software implementation of CP-OFDM can be represented by the system block diagram shown here. Here we can see that the input comes in as a serial binary data stream, which is converted to parallel before being modulated according to the 4-QAM method. The signal is then transformed into the time domain via IFFT. Next, the cyclic prefix is added to the signal. The cyclic prefix is usually a repeated section of the signal which absorbs into simple interference. The signal is then converted back to parallel before finally having a training sequence of 2 consecutive Barker sequences of length 11 added to it and being sent through the channel. The channel used in all of the software simulations was a simple additive white Gaussian noise or AWGN channel with induced CFO. When the signal arrives at the receiver, the first thing that happens is that the Barker sequences are removed and the CFO is estimated. This value is used to do CFO compensation on the signal in the time domain. At the receiver, the signal is first converted back to parallel, then cyclic prefix is discarded. It is transformed into the frequency domain via FFT, then demodulated from 4QAM. Then it is converted back to a serial data stream. At the end of the transmission, the initial and received serial data streams are compared and the bit error rate is calculated. The second system to be implemented in MATLAB is the PCC-OFDM system with training sequences. As we can see on the block diagram shown, this system is quite similar to the CP-OFDM system, however it does not have blocks for adding and removing the cyclic prefix. It does however need a different block which maps the data onto weighted subcarriers in the transmitter and demaps them from weighted subcarriers in the receiver. The subcarrier mapping and demapping occurs in the frequency domain. This is why it is before the IFFT in the transmitter and after the FFT in the receiver. The final system implemented in MATLAB is the PCC-OFDM system with blind CFO estimation. The system is quite different from the previous two systems and has a lot more processing in the receiver than in the transmitter. The transmitter is almost the same as that of the previous system except that it does not add training sequences to the signal. When the signal arrives at the receiver, it is first converted to parallel before being transformed into the frequency domain via FFT. Once in the frequency domain, the subcarriers are separated and the CFO is estimated using the equation previously described. Once the CFO is estimated, this value is then fed into a CFO compensation block along with the original received signal. The reason why there is so much more processing in this system is because the CFO must be estimated in the frequency domain but compensated for in the time domain. After CFO compensation, the signal is once again converted to parallel and transformed into the time domain, before the subcarriers are separated and only the signal from the +1 weighted subcarrier is kept. After this, it is demodulated and converted back into serial and the bit error rate is calculated. These three graphs show the resulting BER versus SNR curves from each system being implemented with an induced normalized CFO of 0.1. Although all three systems work, it is obvious that blind CFO estimation technique does not perform as well as the Barker sequence method. The blind CFO estimation technique bit error rate levels off just under 0.01 at an SNR of about 15 or more, whereas both of the other systems achieve bit error rates less than 10 to the -4 at high SNR values. When comparing the results of CP-OFDM and PCC-OFDM with training sequences, we can see that although they are similar, the PCC-OFDM system does outperform the CP-OFDM system. We can see this from the way the BER value drops much earlier in the PCC-OFDM system, and the final BER value is lower than that of the CP-OFDM system. Here we can see the software-defined radio setup. We have a PC with LabVIEW open. On the left is the transmitter block, and on the right is the receiver block. The PC is connected via high-speed cable to the NI-USRP 2954R device, which we can see is on from the blue light on the right. This device has two pairs of antennas roughly 15 centimeters apart from each other. Now we'll look at the steps of the hardware implementation. First, the CFO value is entered. In this case, it is 200 Hz, which is equivalent to a normalized CFO value of 0.2, considering the subcarrier spacing in this system is roughly 1 kHz. Next, both the transmitter and receiver blocks are run, and we can see that the received signal is affected by the carrier frequency offset. Here we can see that the average CFO estimate is 200.06 Hz. This value is then entered into the CFO compensator. The system is then run again with the CFO compensation, and we can see that the received signal is almost perfectly compensated since it no longer has any rotation present. The results of the hardware implementation are shown here. In this case, the CFO introduced was 100 Hz, which is equivalent to a normalized CFO of 0.1. The signal constellation on the left shows the received signal without CFO compensation. We can see that the CFO estimated was 98.3964, which is an error of about 1.6%. The estimated CFO is then fed into the CFO compensator, and the signal constellation on the right shows the received signal after this CFO compensation. We can clearly see in this signal constellation that no errors will occur from the received signal as each point is in the correct quadrant. Even though CFO estimation was not perfect, we cannot tell with the naked eye that there is any remaining carrier frequency offset in the received compensated signal constellation. It can be concluded from the investigations which were carried out over the course of this project that PCC-OFDM is better for the 5G scenario due to its low out-of-band emissions and better performance in an asynchronous environment. Also, the blind CFO estimation technique works, but not as well as the Barker training sequence CFO estimation technique. And finally, the PCC-OFDM with blind CFO estimation was successfully implemented on a software-defined radio testbed.